Alright, so here we have our first practice problem. Um, Basically, what you have to do is find the oscillation period for the broadcast of a 130.6 megahertz FM radio station, but the answer has to be in nanoseconds. So, well, we're gonna have to do a little bit of unit conversion. So, I have the conversions right here. 1 megahertz equals 1 million hertz, and 1 second equals 1 times 10 to the 9th nanoseconds. So basically, our let's convert to hertz. So our frequency should be 130.6 megahertz um, times 1 megahertz, and this should be capital M, and then 1 times 10 to the 6th hertz. And then we know that the period and the frequency are just reciprocals of each other. So when you calculate the period, you should get something really small, like pretty much you're gonna get 0.00000 zero 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 7 6 5 6 9 6 8 seconds. Let me just double check. Alright. Yeah, so now what we have to do is we have to convert this into nanoseconds. So um, we get um, t right here times 1 second times 1 times 10 to the 9th nanoseconds over 1 second. So then the units cancel out. So you should get an answer of 7.656968 nanoseconds. It's a spring, 20 centimeters to the right. So let me just draw that out. So like this is our glider, and then this is our equilibrium position, and then here's our spring, and then this is 20 centimeters. So it's pulled to right and released. It makes 15 oscillations in 10 seconds. What is the frequency, the max speed, and the position and velocity at 0.8 seconds? So it's pulled back 20 centimeters, right? So it is pulled back as far as it can. Therefore, it is the amplitude, you know. So A equals 20 centimeters, right? Because you're pulling it back, but a certain amount of distance, and when it oscillates, it's gonna it's not gonna go farther than that distance without an external force, assuming again it's not friction. Again, it doesn't have friction. But when you pull it back, you should expect it to go about the same distance, not any farther, and not any close, not any farther away, but not you know um, closer to the equilibrium position unless there's damping. So yeah, it's gonna oscillate between 20 and negative 20. Um, and this is at t equals 0. So if we were to basically get our equation x of t equals a cosine of wt plus v, if we plug in 0, x of 0, so x of 0 is a, so a equals a cosine of w times 0 plus v. So you get a equals a cosine of phi. So you get 1 equals cosine phi. Phi is just 0. So we don't worry about a phase constant. But we do know that this is the amplitude. And we basically have everything we need to find everything that we need. So what is the frequency? So remember what frequency actually means. It means the amount of cycles that you complete in 1 second versus a period, which is how long does it take to complete a single cycle. But in this context, a cycle is the same thing as an oscillation, because an oscillation is just it's just a cycle. You're going from 20 to 0 to negative 20, back to 0, and then back to 20. That is a full cycle, or an oscillation. So we have 15 oscillations in 10 seconds. So we get 15, 1.5, my bad, cycles per second, or oscillations per second. Which is our frequency. Alright, so what is the max speed? So we are given amplitude. And we are given frequency. So without having to use the x or x of t, the position function or velocity function, we can use conservation of energy. So because we're given the amplitude, and we can, and since we only need one variable, but besides the angular frequency, we can solve for it right away. So what I mean by that is, since we were given the max potential energy, we can calculate that with the amplitude. We can find the max kinetic energy, or where the velocity is at its max. So yeah, with the amplitude, we can find the quantity of the total energy. So we get kx squared equals m, and then this should be squared b max squared. So w squared x squared equals v max, which is equal to the square root of w squared x squared, or a squared, my bad. Which is equal to w times a. Well, w times a is just, 2 pi times the frequency times a. So you should get around 60 pi centimeters per second, if I'm pretty sure, because 2 times 1.5 is 3, so that's 3 pi, and then times 20, that's 60 pi. So you get 60 pi centimeters per second for the max speed. So the position and the velocity at t equals 0.8 seconds. So we can actually, so the reason why I brought up the phase constant is because it's going to be useful in this problem. So we're going to use the equation x of 0.8 equals the amplitude, and then the cosine of omega times 0.8 plus phi. We know that the amplitude is 20 centimeters. Cosine. And then we know that the angular frequency is 3 pi. And then we know that time is 0.8, and then we know the phase constant is 0. So when you calculate all that, x of 0.8 should just be around 6.18 centimeters. Alright, so now let's try to solve for v of t, or v of 0.8. So you can solve it in two ways. It's up to you. So you could take the derivative and you'd get this function v max, and then it's sine wt plus phi, and then we don't know the this right here, but we know that the v max is about 60 pi centimeters per second. And then we know that it is the angular frequency is about 3 pi, and then it would be times 0.8 and the phase constant 0. So you can solve it that way, or you can solve it using conservation of energy. So you can use 1/2 kx squared, and then this is at t equals 0.8, and then plus 1/2 mv squared. This is at t equals 0.8, and then you can use the max potential energy or the max kinetic energy. It's up to you, but I'm going to use the max potential. So kx squared plus mv squared equals 1/2 ka, or sorry, did not mean that, ka squared, and then you get ka squared minus x squared equals mv squared, and you get w a squared minus x squared w squared, so equals v squared, and then you get v equals W rad A squared minus X squared. So either way, you should get a velocity of about 100. You should get about a velocity of 179.27 centimeters per second.